Randall will be joining me on stage in half an hour or so. And in the meantime, I'm going to give a short presentation on the role of what I regard as the mammoth in the room in prehistory, which is that we're being told our history and our prehistory without really taking account of global cataclysmic events. And this is most unfortunate, since the role of global cataclysmic events in the human story, it's becoming increasingly obvious, is very, very large. And we should be paying more attention to it if we care for the future of humanity on this beautiful garden of the planet that the universe has gifted to us. We need to pay attention to our future. So, I think everybody's heard of the Mount Toba eruption 74,000 years ago. It was a very, very serious eruption. 2,800 cubic kilometers of volcanic ash and lava were thrown into the atmosphere. 12% more than was ejected by the last Yellowstone eruption. Basically, what is being suggested is that this eruption 74,000 years ago may have almost completely obliterated the human race, that we might have been reduced, our ancestors might have been reduced to just 3,000 individuals around the world. Now, that may not be correct, and like all theories of cataclysm, it has come in for a great deal of criticism and scrutiny, and there's nothing wrong with that. I don't think the criticism and scrutiny has had the ad hominem element that often happens in archaeology. But it's worth keeping this in mind. Actually, we are very focused on impact events at the moment, but if we look at the geological record, volcanic activity looks like a much more dangerous culprit. And let's be clear, volcanic activity and impacts can be connected. A large impact on the surface of the Earth can send shockwaves through the Earth and can set off volcanism as well. But the four mass extinctions are definitely volcanism is definitely implicated, and only one, the extinction of the dinosaurs, we can say definitely it was a cosmic impact. So, other than the Mount Toba event, if we say that anatomically modern humans have been around on the planet for 300,000 years, which we can safely say now. I suspect it's probably much longer than that. But if we say that, then we can say that in the lifetime of anatomically modern humans, there has not been, other than Mount Toba, there has not been a volcanic event which has threatened the future of the human species. In a world which humanity was present, there's just not been any extinction-level volcanic events, but there have been significant asteroid and comet events. So how can we get a sense of the size of the force of cosmic impacts, and perhaps comparing it with the aftermath of nuclear warfare might give us an idea. We're looking at Hiroshima on the right and Nagasaki on the left after the explosion of those two very small atomic bombs. The explosive effect of each was about 15 kilotons. That's 15,000 tons of TNT. And Nagasaki was about 25 kilotons, 25,000 tons of TNT. Let's compare that with Chicxulub, the impact that destroyed the dinosaurs. As much explosive energy as 100 teratons of TNT, 4.5 billion times the explosive power of the Hiroshima atomic bomb. It was the beginning of the end for the dinosaurs, as we've seen. And again, with the Younger Dryas impacts, we see, just as with the dinosaurs, mass extinctions taking place all around the world. And on this occasion, it's very clear, and as Alan helped us to understand yesterday, we're not dealing with one single big impact. We're dealing with a scattergun of smaller impacts all around the world. There may have been big impacts on the North American ice cap. We do suspect that. But what we've got definite evidence for is the Younger Dryas boundary layer and the impact proxies within it. and we've talked about Abu Huraira. Heat sufficient to melt quartz, and quartz melts at 2,200 degrees centigrade. And of course it had a huge effect in that area. Now, Alan mentioned yesterday the Tal al-Hammam study and the suggestion that a Tunguska-sized airburst destroyed Tal al-Hammam, and that this may have been the biblical Sodom. And they're talking about a Tunguska-sized airburst. And let's just look at Tunguska again in Siberia. Altitude of 5 to 6 kilometers, flattened, 80 million trees. A very serious event if it had taken place over an inhabited area. How many megatons was Tunguska? Estimated to between 10 and 40 megatons. And the energy of the explosion is estimated to have been equivalent to the explosive force of as much as 15 megatons of TNT, 1,000 times more powerful than the atomic bomb dropped on Hiroshima. So these events are very, very serious when they happen. And the most recent that we are all aware of was Chelyabinsk. And that's a bit of the Chelyabinsk impactor. It's been slightly, you can see that the top end of it is narrower than the bottom end. That's because it's been oriented by passage through the atmosphere. The atmosphere has burnt it off into this almost pyramidal shape. And here's Randall to talk about Chelyabinsk.
Chelyabinsk, it happened in, was it 2013? It detonated like 15 miles up, but it still caused 1,500 injuries. Nobody was killed, but it caused 1,500 injuries, some of them serious, and it also damaged 7,000 buildings. And I don't know if you've ever seen some of the video clips of that, but the sound wave, the shock wave, is pretty mind.
Where did it hit?
It's a little town called Chelyabinsk, so it was not anywhere close to the magnitude of the Tunguska object. Mm-hmm. But there's a possibility that it also was part of the same torrid meteor stream. There's a paper that just came out on new studies of the torrid meteor stream. They've actually referred to it as the smoking gun for the Younger Dryas event.
And yes, we're talking about the torrid complex. Very likely, indeed, that the Tunguska event was an object that fell out of the torrid meteor stream. Yeah, we are now getting the authorities admitting that Earth could be at risk of meteor impacts. We might have wrongly assumed we're in a safe era. I just want to show a few of these wake-up calls from the universe. 2013, Chelyabinsk. 2015, unexpected asteroid flyby this Halloween. If it's happening at Halloween, it's almost certainly a torrid object. 2016, huge comet unexpectedly whizzes past the Earth. Hours after discovery, asteroid swept by. 2016, asteroid zipped through Earth's shadow last night. Rerun asteroid buzzes Earth in a second close shave of 2017. And it goes on through 2017. Gibraltar-sized space rock passes Earth. Nail-biting near miss with bus-sized asteroid. A close shave from an undetected asteroid. I mean, is the universe sending us messages? Are we being told that we should be paying attention to something? Another Tunguska-sized asteroid makes a surprise flyby. Small asteroids buzzing Earth this weekend. It keeps on going on. 2019, NASA asteroid warning this colossal asteroid will skim Earth today. Astronomers spotted this is 2019, a car-sized asteroid just hours before impact. 2019, asteroid surprise close approach illustrates the need for more eyes on the sky. Yes, definitely it does. And so on and so forth. August 2020, March 2021, record number of asteroids seen whizzing past Earth in 2020. Asteroid the size of the Great Pyramid of Giza just flew safely by Earth. 2021, more of it happening. And then I stopped keeping a record after 2021, but here's a kind of summary. Asteroids which came closer to Earth than the Moon in 2022 by time of discovery. That's the red bit of that chart. 80 asteroids came closer to the Earth than the Moon in 2022. In 2023, it was 62 asteroids that came closer than the Moon. And in 2024, after closest approach, it was 65 asteroids. In other words, we are sometimes not seeing these things until they've gone by. And that is not necessary. We do not have to face doom and gloom because the universe can be a dangerous place. We are an intelligent and innovative species. We are capable of solving this problem. Actually, we could sweep the skies clean of everything in the near-Earth environment that could harm us if we chose to do so. But unfortunately, we're locked in such a state of tribal war in the world today that our leaders are spending, whichever country they live in, are spending much more money, vastly huge orders of magnitude more money on so-called defense, which is basically just another word for aggression, and not defending the Earth from the random dangers of the universe. This is a choice we're making. We don't have to face another Tunguska or another dinosaur event. We can do something about it. It's just a choice. It's just a choice that we make as a species. And it's unfortunate that we're not able to make these choices in a rational way, that tribal instincts in humanity lead us to target one another rather than to look for the collective future of the human race. Because we're all human beings. It doesn't matter which tribe we come from. We're all the same. We all need love. We all give love. We all love our kids. We all have hopes, fears, ambitions. It doesn't matter where we live, what religion we belong to. Fundamentally, what unites us is far, far, far more significant than what divides us. And, and this issue with the way we're relating to the universe is an example of how we're getting our priorities seriously, seriously wrong. And then, of course, the asteroid hits and near misses you've never heard about. So many of those. It just keeps on going on. November 21, the Tunguska. We're talking now about the Torrid meteor stream again. And the work of Dr. Emilio Spedicato, who's a mathematician at the University of Bergamo, together with Victor Klube and Bill Napier, looking at the Torrid meteor stream. It's clear that the Torrid meteor stream is made up of filaments of debris. Imagine a huge tube surrounding the entire solar system, and that tube is 30 million kilometers wide, and that is the Torrid meteor stream. And in it, there are filaments of debris, which are not potentially harmful, but there are also filaments of debris that are indeed potentially harmful. And the calculations of Emilio Spedicato are that before 2040, we are going to be entering one of those very lumpy, dangerous filaments of the Torrid meteor stream, and we're going to be passing through it twice a year. And he's urging that we pay attention to this unique complex of debris, which is undoubtedly the greatest collision hazard facing the Earth at the present time. We started seeing reported in the media some news about the dangers of the Torrid meteor stream, which I'd been drawing attention to for years before that. There seemed to be a growing awareness of the Torrid meteor stream, but then now there's been the usual backlash to that. And the critics, as Alan told us yesterday, have piled in on the Comet Research Group and tried to say, no, there's no real danger, there's no real threat, nothing to worry about, guys. Catastrophism in context of geology and Earth's history is often contrasted with uniformitarianism. Uniformitarianism meaning it's almost a philosophy of science that as we observe the Earth today, the processes that we see today are the same processes that we saw in the past. Nothing very radical or dramatic suddenly happens. We shouldn't expect it to happen. It's going to all unfold in a nice, friendly, polite, nurturing way. That's uniformitarianism, but catastrophism believes that big, violent events cause quick, large changes, while uniformitarianism says these changes occur very slowly over long periods. So I want to look at the issue of J. Harlan Bretz, great geologist, 2nd of September 1882 to 3rd of February 1981. I was introduced to J. Harlan Bretz's work by Randall. We're looking at a remnant of a lost landscape here, this island of ancient soil crowned by a crop of wheat, survived the Ice Age floods that sculpted the region, known today as the Channeled Scablands. Bretz was one of those scientific rebels who wouldn't be told what to think by other scientists, and he believed the evidence of his eyes. And he did this most intense, protracted investigation into the Channeled Scablands of the Pacific Northwest. Began that in 1909. Experts couldn't give him any explanation of the giant potholes in the Quincy Basin, or indeed in many of the other bizarre features. And the mystery inspired him to train as a geologist, and he did, and he qualified. And he went back as a tenured PhD geologist to study the Channeled Scablands again. And the conclusion he came to after all those years of work, studying the nature of the landscape, the deep scars, the huge buttes and mesas left isolated, the only possible explanation, he said, for all the region's features was a massive flood, perhaps the largest in the Earth's history, a debacle which swept the Columbia Plateau, ripping soil and rock from the landscape, carving canyons and cataracts in a matter of days. All other hypotheses meet fatal objections. That was his view. And this was geological heresy. He was talking about this in the 1920s, at a time when uniformitarianism was the dominant view. He, of course, came in for massive series of attacks. From the point of view of other geologists, it didn't matter how meticulous Bretz's research was or how sound his reasoning might be. He seemed to be advocating a return to geology's dark ages, when scientists used catastrophic explanations. They didn't want to hear that anymore. He gave several lectures expressing his view that we're looking at the results of one horrendous flood. The geologists were aghast in the same way that a room full of physicists would be upon hearing a colleague explain how he had made a perpetual motion machine out of old popsicle sticks. So there was a feeling that what Bretz was proposing just was impossible and it should be ignored. His radical conclusion of this single massive flood, perhaps the largest in the history of the Earth, particularly outraged and alarmed the pedestrian minds of the profoundly conservative US Geological Survey, who was committed to the uniformitarian view. Universally, he was rejected, he was condemned, he was told that he was wrong, that he didn't have enough evidence, that it was almost accused of being a hoaxer. And it wasn't until the 1950s, it wasn't until then, that the geological establishment began to recognize that Bretz had actually been right all along. That what we're looking at in the Channeled Scablands is massive evidence of flood damage. And the plaudits began to come in, and he took a group of previously hostile geologists on a field trip, and he showed them the features that led him to his conclusion. And afterwards, they sent him a telegram acknowledging his early insights and claiming, "We are all catastrophists now." Bretz's reply, "Be assured that after 30 years and 30 papers in self-defense and more than 30 people who vigorously denied my theory, it did my heart good, like medicine." And it was the toxic antipathy of the gradualists that made Bretz a pariah and a social outcast. In 1979, however, the GSA finally reversed its position and bestowed upon him the highest award in the field of geology, the Penrose Medal. Bretz was 96 years old at the time, and on receiving the reward, he reportedly told his son, "All my enemies are dead, so I have no one to gloat over." He was truly a great man. And what brought about the transformation from pariah to poster boy? The problem all along had been his insistence that the Channeled Scablands had been gouged and plucked by a single massive flood. That challenged the ruling paradigm, and he was never able to offer a satisfactory source for the immense volume of flood water. And what happened was that in order to get acceptance of his theory, he had to kind of back off a bit. And the theory that it was floodwater, that was fully accepted, but they still couldn't bear the idea that it might have been one single massive event. And so they wanted him to transform his theory, which was cataclysmic, catastrophic in nature, into a gradualist theory by saying we're looking at the effects of multiple floods that took place over thousands of years. In fact, the current scenario is that there were more than 80 floods. And National Geographic now comfortably embrace that idea. And so we witness Bretz's raw catastrophism being quietly transformed back into a form of polite gradualism. So this is the Channel Scablands. Extraordinary area, and littered with these glacial erratics. Features of the landscape that are hard to explain in any other way than giant flooding. And they've always been difficult to account for by the multiple floods from Lake Missoula model. So Santha and I made a trip with Randall Carlson across the Channel Scablands a few years back. It was an amazing trip, and it was wonderful to see the Channel Scablands through Randall's eyes. I think he's a worthy successor of J. Harlan Bretz, as a matter of fact. And he is still bringing to the table views that mainstream geologists are unwilling to accept. But here we're looking at Great Falls, this waterfall, this former fossilized waterfall, which appears to have been created in less than a couple of weeks. And to give you the scale, this waterfall, this fossilized waterfall, that's the Niagara Falls set against the back of it. So we're looking at something truly gigantic, something that we don't see on the Earth today. On the left, these are current ripples. As the tide recedes from a beach, the water seeps out and it leaves behind these ripples. So it's fascinating, very far from the sea, to find current ripples in the Channel Scablands, the Camas Prairie. You see, there's a car for scale, and these are all ripples in the landscape caused by the recession of those floodwaters. You can get a sense of the scale of it here. These ripples are 30 or 40 feet high. This obviously was a gigantic event, and it was a single event. This is a so-called glacial erratic above the town of Wenatchee. It weighs an estimated 13,000 tons. It comes from more than 100 miles away. How did it get there? Well, the answer is it got there in an iceberg. And the iceberg was rafted on the flood, and it was carried 100 miles on the flood, and finally it was dumped on this hillside, and the ice melted away, and the boulder is left in place. And it just gives you a sense of there's me and Randall in front of it, both slightly younger than we are today, and there's me on top of it. It just gives you the sense of the power of this, that something this big can be carried in an iceberg on flood, and it's not alone. There's hundreds of them, hundreds of these massive boulders. So these are not just flood waters. These are churning waters filled with icebergs, filled with ripped up forests. There's mass in those waters. It's not just liquid. It's a solid, deadly, dangerous slurry that's pouring down. And you can see examples. These erratics are scattered all over the region, all left behind by retreating floodwaters. Boulder Park. The Willamette meteorite is interesting. It fell on the North American ice cap and was transported in an iceberg to the Willamette Valley, Oregon, during the cataclysmic Younger Dryas floods 12,800 years ago. It was known and venerated by the Clackamas tribe, who called it Tamanawas, before being seized by the Oregon Iron and Steel Company. According to tribal legend, Tamanawas was sent to Earth as a representative of the sky people, exemplifying a union of sky, earth, and water. It is an oriented meteorite again. If you see this shape, that's called an oriented meteorite, and that's because as it's entering the Earth's atmosphere, the atmosphere burns away the front part of it and turns it into almost this pyramid shape. In fact, there's very serious evidence that the origin of the pyramid form in ancient Egypt was based on what is called the Benben, and this was a meteorite, an oriented meteorite, that the ancient Egyptians saw this coming from the sky. They saw the pyramidal shape and reflected that in the pyramids. So the truth is that Bretz never really abandoned his model, even though he had to accommodate the prevailing opinion. But the unique assemblage of forms described as the Channel Scablands records a unique episode in Pleistocene history. Clearly, special causes seem indicated. So now I'll ask Randall to join me, and we will have a conversation. Thank you. Okay. So, my dear friend, Randall Carlson. And Randall has taught me so much about the geologic history of the Earth and how we cannot disentangle the geologic story of the Earth from the story of humanity. These have to be absolutely connected. And it was a great privilege to travel through the Channel Scablands with you.
Really good memories.
I think we should do another journey.
Pardon me?
I think we should do another journey to the Channel
I'd love
Scablands.
to.
I'd love to go see them again.
You know, next month, Bradley and I have organized. You remember Bradley?
Yeah.
Yeah, of course. He was our driver on the trip and tremendously helpful in organizing these expeditions.
Yeah.
So we're going to do follow the Great Bonneville Flood up from Bonneville Basin in Utah north into Idaho, and then we'll follow its route along the Snake River.
Right.
Last fall, we did a trip looking at the Missoula floods, and Bradley arranged for us to get into a large gravel pit, a large gravel quarry, and we got the tour of the place. Mm-hmm. What was interesting about this gravel quarry is it's right there at a place called Tammany Bar. And what happened when the Missoula floods came down, you had a slide up there of Palouse Falls, right? So that was part of the Cheney-Palouse Scabland track. That water came down, I believe, out of Canada, hit the Snake River. It backflooded nearly 150 miles up the Snake and finally reached its distal flow right there at Tammany Bar. Right. So what happens is if the water is moving upstream, it's slowing down. And as it's slowing down, it's depositing its sediment, right? So what happens is at the distal point of a backflow, you're going to find really fine-grained sediment, whereas at the proximal end of the flow, you'll find the big boulders, right? Well, so you had the Bonneville flood coming north up through Hell's Canyon, the deepest canyon in North America. Yeah. As it discharged from the mouth of the canyon, it laid these thick gravel, thicker than this room is tall, right there at Tammany Bar. And if you go there, you can see these dark gray, very coarse, bouldery deposits from the Bonneville flood coming north, sandwiched, almost like frosting on the top of it. You see these fine-grained, buff-colored silts that were the backflood sediments of the Missoula flood. Right. And they're juxtaposed right on top of one another. Now, I think we had first seen that when I think we went by there as early as 1998. And I remember seeing that it looked like there was a direct contact between the two flood deposits. Yep. So what I became interested in was what was the timing? Was there a hiatus between the two events? Yep. Well, so getting into this quarry last fall, I was able to, they had a pit that was excavated. We were able to go down in that pit, and under the Bonneville was more Missoula flood, backflood silts. So you had Missoula flood silts, you had the Bonneville coarse stuff coming up ultimately out of Utah and southern Idaho, and then on top of that you had more Missoula flood sediments. The sequence gave the appearance that essentially, and that's what I was looking for. I predicted that we might find, if we could get access to the base of the Bonneville flood sediments, we would find Missoula sediments. Yeah. And there they were. What that suggests is that these two events were happening simultaneously.
Simultaneously, not multiple separate floods.
Correct.
Yeah.
Simultaneous. Now, Missoula flood, the theory is that you had a great glacially dammed lake. Yeah. The ice dam gave way, and this happened, like you said, repeatedly.
Up to 80 times, apparently.
Up to 80 times, which personally I think is ridiculous.
Me too.
Okay. And then, but the Bonneville flood, you had this gigantic lake, over 20,000 square miles. You know, the Bonneville Salt Flats. How many of you guys know what the Bonneville Salt Flats where they test? Yeah. So that was the lake bottom. And if you're traveling in, say, Salt Lake City, if you look to the east up on the Wasatch Mountains, you're going to see two great shorelines etched, right? One of them is 1,000 feet above the valley floor, and that was the depth of this temporary gigantic lake that formed. It rose up. I suspect that there was probably a seismic event, fractured a sedimentary rock dam to the north. That gave way, and over the next 3 to 4 months, 350 feet of water drained out. Mm-hmm. And so when you see the two shorelines, you see one that's above roughly 1,000 feet above the valley floor, and then about 350 feet below that, you see a second shoreline, right? So this flood wound its way through, carved out the Snake River Canyon, over-deepened Hell's Canyon, and then, I believe, met the Missoula floodwaters. But unlike the Missoula floodwaters, so you had these two giant lakes. They both break through. One's a sedimentary rock dam, that's Bonneville. One is supposed to be a glacial dam. Now, the Bonneville Lake was not being fed directly by glacial meltwater. So it had to be rainfall.
Yeah.
It had to be intense rainfall. It had to be torrential, prolonged rainfall, because that rose very quickly up to that 1,000 foot above the valley floor. So what I was believing was if we could show that those two floods were contemporaneous, now what we've done is we've expanded the scale and scope of that terminal ice age catastrophe. So being able to get in there last September and see that for myself and see that I had imagined that if we could get to the bottom of those Bonneville flood sediments, we might see Missoula flood. Now,
You were testing your hypothesis, basically.
Pardon me?
You were testing your hypothesis.
Yes.
Yeah.
Yes.
Which is the right thing to do in science.
Yeah.
Yeah.
And you know, the quarryman who was giving us the tour there, I asked him, you know, I mean, when you are excavating here, do you find, you know, I mean, so he was sure they had a pile of boulders that they had pulled out of that had been washed up out of Idaho and probably stripped out in the cutting of Hell's Canyon. So we're going to do this tour in November.
You're going to take a group.
Pardon?
You're going to take a group.
We're going to take a group.
And explore the landscape.
And it's almost sold out. I think we have 3 or 4, maybe 5 seats left.
Right. So if anybody's interested, how do we access your
just
your
randallcarlson.com, and I got links. And
check out randallcarlson.com. Traveling in these landscapes with Randall is an eye-opening experience, to say the least, and I highly recommend his tours.
Thank you. Well,
we were going to one of the issues with the multiple floods model is that when we look at all of the damage in the Channel Scablands, we find that the mainstream explanation doesn't connect it at all to the Younger Dryas impact. It seems to suggest that it happened before that.
Correct.
And I know that you're not happy with that view, and I'm not happy with that view either. There's no doubt that glacial lakes did release waters.
Absolutely.
That's for sure.
That's for sure.
But was it enough waters to do this damage? And I think this is where I come back to the Younger Dryas impact hypothesis and the notion of a couple of large bolides hitting the North American ice cap and releasing much more water. And of course, as that water comes forth, it's going to fill up those glacial lakes and force them to release their waters. Yeah.
Yeah.
What do you think about the timing of these events?
My thinking is still evolving. One of the things I've looked at is, you know, John Shaw referred to CREs, catastrophic rise events, which were sudden pulses of sea level rise. You know, that 400-foot rise in sea level from the late glacial maximum to the early Holocene was not a smooth curve.
No.
It was punctuated by several extreme discharge events from the melting glaciers into the global oceans.
Yeah.
The first one now, the earliest one, Meltwater Pulse 1A, is dated at 14,600. The Meltwater Pulse 1B is dated at 11,600, which is the top of the Younger Dryas, the 1200, 1300 year.
When Randall says the top, this is speaking in a sense in archaeological terms. What's higher up is younger, and what's lower down is older. So the top is younger.
So the Younger Dryas, is a little less than 12,900.
Something like
the
that,
latest dating,
Yeah.
right? Now, the question is there evidence of the floods associated with the Younger Dryas? And if you're familiar with the work of James Teller,
A little.
okay, you should go ahead and look into his work.
Tell us more.
Pardon me?
Tell us more.
Okay. Well, he's been studying. He's probably the foremost leading expert on Lake Agassiz, which was this gigantic meltwater freshwater lake.
Yeah.
It was so big that it would take you days to sail across it.
Yeah.
When you're out in the middle of the thing, you wouldn't have seen any shorelines.
And that's further east than the Lake Missoula.
Yes, that would have been meltwater from the Laurentide ice sheet.
Yeah.
Whereas the Missoula would have been meltwater from the Cordillera.
From the Cordillera, yeah.
Right.
Yeah.
Well, so he's dated that there was a major outburst flood, both to the north, that basically carved out the channel, the canyon that Mackenzie River now flows into the Arctic. There was also, at the same time, an outburst to the south, and you and I visited the outburst on our tour. We stopped at the outburst point of Lake Agassiz as we were crossing the South Dakota-Minnesota border. It's right there.
Right.
And it was also a bird sanctuary. I don't know if you remember the bird sanctuary. I know you were wiped out, man.
I'm always wiped out. The bird sanctuary doesn't ring a bell, but other aspects do.
Santa will definitely remember
She
the
will,
bird sanctuary. It was like they were just hallelujahing. It was amazing. But anyways, right there, it's Big Stone Lake.
Yeah.
And I got a slide, actually, of you walking over looking at some of these gigantic boulders that are laying on the landscape. And this was the outburst point, the southern outburst point of Lake Agassiz.
Right.
The northernmost was what led into the Arctic Ocean via the Mackenzie. Teller dates that at precisely the lower Younger Dryas boundary.
I see. So he's
That's
he's dating it to the beginning of the Younger Dryas.
At the beginning of the Younger Dryas.
Which kind of, it's difficult to resist the conclusion that we're looking at cause and effect here. Not just a correlation, but...
And I'm of the mind that we might need to be looking at maybe several huge melting events.
Yeah.
Maybe not just one.
I felt for quite a long time that the 12,900 or 12,860 year ago event was just the beginning of the story.
Yeah.
That we were passing through a particularly dense part of the Taurid meteor stream at that time, and it's reasonable to expect that it wouldn't have been confined to one episode of impacts. There would have been multiple episodes of impacts over that 1,200-year period, perhaps more.
And certainly we had the potential. I mean, in the model of the giant comet hypothesis, that somewhere maybe 26 to 30,000 years ago, I think, referring to Klube and Napier's work. You have this giant comet comes in from wherever, I'm presuming the Kuiper disk, because the Taurids are very close to the ecliptic. Comes in, undergoes a hierarchy of disintegrations, litters its elliptical orbit with debris. The debris is not, at that point, early stages of the formation of the meteor stream. It's not going to be uniformly distributed. There's going to be clusters, clumps. And it's very possible that Earth could have crossed that stream multiple times, and there could have been several impact episodes. So at 14.6, I'm thinking that some of the dating I've seen for the Missoula floods might actually go date to 14,600. But I'm not settled on that yet. We need more data. We need more information.
Sure. It's an ongoing study.
Yeah, and some of the dating, I would question optically stimulated luminescence and the production of beryllium-10 and carbon-14. We may not be getting an accurate depiction of the concentrations of these isotopes into the atmosphere simply because it's in the nature of a cosmic impact event, right? It may be biasing the data to several millennia too old. And the other thing I'd kind of like to address is this, 40 to 80 or more floods. Now, in that model, like what Graham said earlier, they're desperately grasping at some kind of a uniformitarian model.
Yeah.
And we have seen in recent couple of centuries repeated episodes of glacial outburst floods, where particularly because, you know, in the roughly from 1300 to about the middle of the 19th century, Earth was undergoing a climate regime called the Little Ice Age. And during the Little Ice Age, glaciers grew to their greatest extent that they had been since 10,000 years ago. So that gave us a golden opportunity to witness firsthand what happens when these large swollen glaciers begin to melt back. Mm-hmm. And they formed proglacial lakes. Oftentimes these proglacial lakes were held in by ice dams, and those ice dams would give way, and you would have a locally catastrophic flood. Mm-hmm. Typically, though, and I made a pretty in-depth study of many of the modern outburst floods, the volumes, the peak volumes and the peak discharges typically are in a range of less than 1,000th, sometimes only a 10,000th of the volume of the Missoula outburst.
Right.
Because we're being, Victor Baker calculated in 1973 when he was the first one who had a hydrologist's background, mm-hmm. who came in and looked at the evidence in the valley north of Spokane,
yeah.
and calculated that the peak discharges were between 700 and 800 million cubic feet per second. Wow. So he doubled mm-hmm. Bretz's peak discharge.
Yeah. Yeah.
And I think that was kind of the beginning of a new generation of studies on the Missoula flood. But right. what's happened since then is, like you said, a number of the geologists have really tried to fit it into the uniformitarian model, which says we try to explain past events by looking at analogs in the present.
Yeah.
And so what they did was just extrapolate up by orders of magnitude and said, well, this is just a larger version of what we've seen in Alaska, in British Columbia, in Tibet, in mountain regions around the world. And so then, to me, where it went wrong was because if the models now, in a sense, almost never go beyond the mountain valleys of western Montana. Graham had a graphic up there which showed eastern Washington, which was the Channel Scablands, and then western Montana, where the lake actually was. And there is a region right there at Montana-Idaho border, just east of Lake Pend d'Oreille, which is a lake that's over 1,100 feet deep. It's so deep, in fact, that they test scale model Trident submarines there. Now, at this place is where the ice dam is generally placed. Now, in 1998, when I went out to really do my first 2 or 3 week field excursion to see all of these sites for myself, one of the geologists I'd been reading was Roy Breckenridge. So I looked up Roy Breckenridge in his office at the University of Montana there in Moscow, Idaho, or University of Idaho. He's in Moscow, Idaho, whichever university it was. Anyways, we had a very interesting conversation for about an hour, and I said, I'm on my way up the Clark Fork River, and I want to investigate the area where was the ice dam? Where did the ice dam meet the lake water? And I thought, I've read your papers and stuff, and basically the upshot of it was, he said, I can't tell you. I don't really even, he says, essentially what he expressed to me, and I don't remember the exact words, but the idea he expressed to me was, after studying years and years, he now could not conclude that there was, in fact, an ice dam.
Right. It was always a theory, always a...
Yes. And so the idea, if you got this ice dam holding in water, now if you look at modern examples, what you'll see is ice dams fail once the water gets 100, 200 feet deep against the ice dam.
Yeah.
Some of the deepest ones I found maybe were up to 300 feet deep.
Right.
They didn't last long. Here we're talking about water 2,100 feet deep.
Right.
Now that means at the heel of the ice dam, pressures are going to be 950, 960 pounds per square inch. There's no way, there's no way, guys, that ice, particularly temperate ice, is going to be able to withstand those kind of pressures.
Yeah.
It's going to fail long before water gets 2,100 feet deep.
Yeah.
But it was 2,100 feet deep.
Right.
You can
tell from the coastlines.
Yeah.
Yeah.
Yeah. So I concluded that it was a flash melting on a large scale. So in 1999, Bradley and I, with a couple other buddies, we went up to Prince George, British Columbia, which is where I believe the source of the floods.
Yeah.
And I'm preparing now a whole presentation to show. So we made subsequent 2 or 3 other trips up there in that region, and I've collected an enormous mass of evidence that I believe demonstrates that the source of the water was rapidly melting Cordilleran ice sheets. Lake Missoula was not really a lake in the sense of a static body of water. It was like just a temporary holding pond.
Yeah.
And 600 cubic miles of water washed in there and then eventually flowed back out.
Yeah. Yeah.
And that's where, and there's a couple of new studies that have come out. Now, one of the things that we did was we made a traverse from the headwaters of the Fraser River, which flows down and discharges there at Vancouver, Canada. Vancouver, Canada is built on this massive delta that's splayed out from the mouth of the Fraser. And we did video footage. I got photographs all the way down that Fraser River showing catastrophic flood effects. Well, a paper's just come out, 2 papers, one in 2021 and another one just this past year, documenting catastrophic huge flood all down that Fraser River. The point, when you trace that up, you get to this zone up there where you have the headwaters of the Columbia, the headwaters of the Okanagan, the headwaters of the Fraser, all up there on what's called the Nechako Plateau, and then you have the Rocky Mountain Trench. I think all of those, which were basically north-south trending valleys, were conduits for gigantic meltwater flows.
Right.
Then the question becomes, okay, so it appears that right up there near Prince George, British Columbia, you had an epicenter of catastrophic melting.
Yeah.
Where does that point us directly to an idea?
I feel it points us to an impact.
Absolutely, absolutely.
Yeah. And is there anything in the dating that would rule out that being connected to the Younger Dryas event?
The dating, interestingly, the dating of that flood was 11,600.
Okay, so it's a Younger Dryas event. It's the
Younger Dryas.
The end of the Younger Dryas.
Event.
Intriguing. So Randall, I would say you're a catastrophist, right?
I would call myself a catastrophist. Yes.
Yes. Let's look at the role of catastrophes in human history, and what's your view about the way that academia, science, archaeology has treated the role of catastrophes in the human story? You know, we have these big histories of humanity, but you very rarely hear anything about anything much more than a local flood. And when archaeologists are confronted with the phenomenon of more than 200 flood myths all around the world, right. They say, oh no, this was just those poor, simple primitives imagining that a local flood was a global flood. Yeah, well, I don't agree with archaeologists on that. I don't think they were poor, simple primitives. I think when they said it was a global flood, they knew it was a global flood.
Yes, and I mean, what you just said is my take exactly. What they've done is they've assumed, well, this was a local flood that got just exaggerated in the retelling. No. That's essentially the model. But like you said, I mean, there have been several hundred accounts, and the parallels between them are striking. The last rambles among the Native Americans, I've quoted this, I forget the exact title of it, but it was, I usually just refer to it as Last Rambles. It's George Catlin. He was a famous Indian artist who spent decades traveling and living with and painting and studying various Native American tribes. And at the end of his long career in his life's work, he writes this book, Last Rambles, and he talks about the diversity amongst the various tribes, the languages, the customs, the symbolisms, their rituals and ceremonies, all of this. But then he says, but there was one thing they all had in common. They all believed that they were descended from the survivors of a great flood. Yeah. Sometimes those stories also involved great fires. Mm-hmm. And I'm thinking, okay, well, is there a naturalistic phenomena? And I think the answer is obvious. Yes, there is a naturalistic phenomena. And we know now from Younger Dryas studies that there were large-scale mega fires.
Yeah. As you would expect, I mean, this is the almost ironic situation with a impact event is that you get floods and fires. It sets off wildfires.
Yeah, and that's what many of the stories.
Many of the stories and traditions from around the world remember colossal floods. They remember colossal wildfires. They remember a time of darkness when the skies are completely dark.
Yeah.
They remember a time of cold. It's icy, frozen cold. There's this overwhelming sense of cataclysm, and not a small local cataclysm, but a very big one.
The Thimble winter of the Scandinavians.
Yeah.
Sounds very much like the Younger Dryas to me.
Yeah.
So we should mention that there was a gradual warming going on from between the older Dryas and the Younger Dryas that got reversed.
Yeah. It was warming up from about 14,000, 15,000 years ago through until the beginning of the Younger Dryas.
Yes, it was warming up, which I think we could probably attribute to the Milankovitch.
Yes.
Nice slow pace of warming.
Yes. Yeah.
But then that's interrupted by this massive spasm of return to cold.
Yeah. The Younger Dryas, when you look at it on the chart, it's a real anomaly.
It is a real anomaly.
It's suddenly, out of nowhere, a trend that has been going on for thousands of years is reversed, and we go back almost to the peak of the Ice Age, really.
Right. Now, circling back to the modern idea of multiple floods, when we look at the history of geology, interestingly, you find that before geology was a standardized academic tradition, virtually all the founding fathers of geology were catastrophists. William Buckland, they didn't all necessarily think the same thing. They had different models, but they were all in their own way catastrophists.
Yeah.
Georges Cuvier, Agassiz, Roderick Murchison, Adam Sedgwick, they were all catastrophists.
Yeah.
And they were not looking, and they came to those conclusions by looking at the landscape free of the lens of dogma.
Yeah.
They're looking in the landscapes spoke directly to them. In England, it was the drift, called the drift.
Yeah.
Looking at these massive deposits, like along the Thames River and other places.
Yeah.
And eventually, by the time after Lyellian gradualism became the dominant paradigm, you had first James Hutton, who actually proposed with the idea that Earth history was much longer. See, when you're trying to cram all of the changes you see embedded in the landscape in like a 7,000-year Earth history model.
The biblical notion that the Earth is 6,000 years old or whatever.
Exactly.
Yeah.
Well, by mid to late 19th century, we've evolved beyond that. Now we have all this additional time to work with.
Yeah.
So the uniformitarian model sort of emerged as an academic discipline about the same time Darwinian evolution, incrementalism, and they sort of complemented each other. Now we've got endless amount of time for species to evolve, and we've got endless amount of time to create a giant cataract or whatever the case may be. And then there was also the contention between, the emerging science, which was primarily based on observational evidence, and its main competitor, which was biblical literalism. And so there was a long controversy. There was a battle between the two sides that was eventually won by the scientific models. But so there was a reluctance. By the time we get to the 20th century and, Brett's, I think the last of the old catastrophists was, his name, it'll come to me in a second. He was still writing papers in the 1890s,
Right.
1900s, early 1900s. And then nobody until Brett's came along, and in the 1920s. But so I think what you had there was James Hutton, and then you had Playfair, and then Charles Lyell basically codified it into a dogma, and that's what became accepted once geology became an academic discipline. And so the fear was, if you start talking about big floods, you're going to try to drag us right back to biblical literalism.
Yeah.
And so that was kind of the conflict there. right? They didn't want to go there because they felt like it was going to be a throwback. Look, we had this hard-won battle, and we finally prevailed after a century or two, and we're not going to go back.
Yeah. Yeah.
And so that was kind of where they were coming from.
Yeah, they wanted to distance themselves from anything
Correct.
that might be,
Exactly.
might even have a sniff of biblical literalism about it. Yeah.
Right. So the idea, I think, that you were referring to, when you talked about the multiple flood hypothesis, see, there you've got the situation where when you say a multiple floods, well, the model was you had this gradual filling of the lake over half a century to a century, and that was filled because you had this gradual encroachment of a lobe of the Cordilleran ice sheet called the Purcell Trench lobe, came south, and where Lake Pend Oreille, if you guys look at maps, look there at the northern Idaho, you'll see Lake Pend Oreille. Lake Pend Oreille would have been right where the ice dam was proposed to be. So you have this gradual encroachment of the ice dam. You have the gradual filling over 50 to 100 years of the lake. It gets, 1,800, 2,000 feet deep, bursts through the ice dam, flows out over eastern Washington, and then the process repeats itself over and over again. But here's the thing. I mean, when you look at glaciers, there's a continuum of glaciers. One end, you've got a polar glacier, which is fast frozen to the ground beneath it. And it's very slow moving. I mean, inches a year because it's so cold and it's frozen to the ground. Then you've got temperate glaciers that are fast moving, but they ride on a base of water. There's meltwater, like a sheet of meltwater under them.
Yeah.
There's no way that you could have had a polar glacier there, because how do you have a polar glacier and right next to it you have 600 cubic miles of water?
Yeah.
That would have actually just been more glacial ice. So you've got a temperate glacier, and it's riding on ice, riding on water. And then on the downstream side of this ice dam, you've got what they're calling Lake Columbia now, which was about 1,300 feet deep. So you've got, at the top end, you've got Lake Missoula, 2,000 feet deep. 30 miles away, you've got the toe of the ice dam. You've got water 1,300 feet deep. Now, how in the world, in my mind, do you prevent hydraulic connectivity between all these bodies of water? And so there was a geologist by the name of C. Warren Hunt. You remember him, right?
I do, yeah.
Yeah, C. Warren Hunt, he was a Canadian geologist, and he wrote a couple of papers in the 1970s in the, the Canadian Journal of Petroleum Geology.
Yeah.
Widely read academic journal. I'm sure many of you in here have read, regularly read that journal. I don't remember how I came upon it, but he had two papers. And he was saying this idea of an ice dam for the Missoula floods is ridiculous.
Yeah.
And he's and in trying to come up with a explanation, he invoked the passage of a cosmic body.
Right. Yeah.
In 1977.
So he's ahead of his time in that respect.
Pardon me?
He was ahead of his time.
Way ahead of his time. So I called him up and had several conversations with him before that first trip to Canada that I made in 1999. He was still alive. I think he was probably late 80s then. And I said, do you still hold to this is 20 years after these papers?
Yeah.
And he said, oh, absolutely, more than ever.
Yeah.
He said, I think that we have to look at some type of a cosmic event.
Yeah. Yeah.
And so he needs to get credit too.
Absolutely, yeah.
Yeah.
So what's happening is that there's a sense that the paradigm is gradually shifting, that the case you've made all along, that the Channel Scablands need to be looked at again, and the whole issue of the dating and how this damage was caused needs to be looked at again. There's a sense that there's some movement in this area, and
I think so.
Yeah.
What's happened now, interestingly, is since I've got a much broader audience, I've had geologists now coming on some of the tours.
Oh, great.
Yeah.
That's good.
And they're totally, and there's a whole younger generation. I've been contacted probably a couple of dozen times in the last 5 to 10 years by, I got inspired by your work, and I'm getting my degree in geology.
Yeah.
And I think you're right.
Yeah.
So I think it's like you said, what is it, one funeral at a time, perhaps?
That's right. It was Alan West. Yeah, yeah.
But, you know, I think that it's all intertwined, this idea, this resistance to a catastrophist model. And it's one thing to admit and to say, oh, great catastrophe, the Cretaceous Tertiary impact wiped out the dinosaurs 66 million years ago. But there's not really the same kind of political implications as you get when you start talking about global catastrophes within the time of humans.
Absolutely. That's the thing. Somehow we can all talk freely about the extinction of the dinosaurs because that doesn't involve us. But stuff that happened 12,000 years ago, that's dangerously recent.
Too dangerously close.
And there seems to be an agenda to minimize the implications of that.
Oh, yeah. Well, frequently, and this is the irony in my mind, oftentimes I get, when I'm attacked online, one of the frequent refrains is, oh, Randall Carlson, he's a climate change denier. And I'm, wait, what? I'm here talking about catastrophic climate change over and over again.
And you're supposed to be a denier.
And I'm really? Okay. I'm still like, okay, I don't think you've listened to any of my lectures, read any of the papers I've posted online. No. You're just regurgitating a political narrative.
Yeah.
Anybody who doesn't fit the established narrative, you know, you're going to get called names.
Yeah, absolutely.
And as soon as you see that's a tip-off, as soon as they start calling you names, you know they don't have an argument.
Yeah, that's right.
They've already lost the argument.
Yeah, they resort to these low tactics because they actually don't have any high tactics.
They don't.
Yeah.
If they did, and usually sometimes I get very useful criticisms because I don't claim to have the final answer. This is a complicated thing.
Yeah.
And it's going to probably take years still to get it all sorted out.
Sure.
But I think we've got the broad parameters now where we have a model now that, you know, there's some parts missing, there's some inconsistencies, but I think we're on our way to really evolving a new model of first Earth history, which was one thing to understand catastrophism, say, in the story of life on Earth.
Yeah.
Now what we're doing is we're bringing it home, and we're asking, what is the role of catastrophism in the story of human civilization on Earth?
Exactly, and that's where the key issues really begin. This is where it really does concern us.
Right, because
this is all of us.
This is where it relates to us, and it's not just academic interest in explaining our past, because the point you were making earlier, this is about our future as well.
That's right.
Yeah.
Randall, tell me a bit about your story. How did you come to be the person you are? Why are you focused on these issues? What's your trajectory been over the years? I think one of the themes that has come out of this event is that we need more eyes on the problem of the past than the official eyes, the so-called accredited geologists or accredited archaeologists with lots of letters after their names who claim to be the sole authorities on any matter. What we're seeing here is that people who don't have those letters after their names, but who get out and do the legwork and are passionate and are committed and really do the research, are bringing new insights that the academics are not bringing. And that's one of the things that I really admire about you. I think it's true to say you're self-taught in this area. Talk to me about.
I majored in geology in college.
Yeah.
And actually, I did. I was recognized as being the outstanding geology student at the DeKalb College where I was studying.
Yeah.
So I got the plaque and everything. Because basically, I'd already been teaching myself geology for 15 years before I actually decided to try to formalize my
So it's
education.
a subject you had a kind of natural passion for. You were drawn to the subject.
Yeah, I mean, I told this, variations of the story before, but growing up in rural Minnesota, we owned some land right on the edge of a lake that was a kettle lake, which you had a big iceberg sitting there in the glacial till. It melted, and of course I didn't know this back then, but I think growing up there in that environment, and right where we lived was at the margin of what's called the superior lobe of the Laurentide ice sheet. So you had the expansion of the lobe, the contraction of the lobe, and it really created a really unique landscape. And I just can remember being very young, 7, 8, 9 years old, just being almost entranced by the landscape. And I had this sense very subtle, but it was a sense that, there's it's almost like it was like a story that it. So one of the things that, there were, a number of different events that I would consider hallmarks. One, we used to go up to the St. Croix River, and you and I went there. It was the last place you and I visited.
Yep.
Were those huge potholes.
Yep.
And those potholes were created by extremely swift-moving turbulent floods that swept through that contraction in the river valley there.
And the pothole will be created by hard objects in the flood, by stone swirling around.
Yeah, first you get the vortex, and then that'll pick up material.
Yeah.
And then that can literally drill. Now that was where we saw those potholes. That was a hard basalt.
Yeah.
But it was like a shelf that was 50 or 60 feet above the modern St. Croix River.
Yeah.
And the water was probably at least 200 to 300 feet deep, gushing through there.
Sure.
And it was like a hydraulic flume almost, because there was a contraction in the valley. So the water is speeding up, it's becoming more turbulent, and you had these, it wouldn't be far off base to call them underwater tornadoes. And they did this and drilled dozens of these gigantic potholes in the basalt there. And that's what we were looking at. I have a great photo of you where I'm in the bottom of the pothole and you're leaning over looking down.
Yeah.
And, but yeah, that was a regular place that we used to go as a kid. And then I've told this story also. Summer of 1969, Flying Cloud Airport was right on the banks of the valley of the Minnesota River. It was southwest of Minneapolis. And they used to have free rock concerts out there. So I would, in the summer of 1969, and I was at one of these concerts. It's probably early. I remember it was a beautiful day. It was a break in the music, and the airport sits on these 250-foot high bluffs. Yeah. And then you look down, and there's this beautiful valley. It's about 3 miles wide. On the other side of the valley is another set of bluffs, right? Kind of the counterpart. And down below, you see the modern Minnesota River, right? And I remember I walked over and I'm standing there looking down at that Minnesota River, and it had entrenched itself into the alluvial floor of the big valley. And I remember just having this impression. It wasn't even a conscious thought. It was just the impression as I'm looking at the river with its two banks, and then I'm standing on this 250-foot bluff, and then there's this other bluff. I had this sort of and I was probably, it's very possible I was in an altered state.
As one does at rock concerts.
Anyways, I had this overwhelming sense that they were like, I didn't know the term scale invariant then. That was years in my future. But so I had the sense that there was this big valley that was essentially, that the modern Minnesota River was just a small version of this big valley.
Right.
And years later, I got into a debate with somebody who had a degree in geology, and I was talking about that. And he was, no. That was millions of years to cut that. And I said, I think you're wrong. And in fact, it was that argument with him, I think, that ultimately stimulated me to actually sign up and start taking geology courses formally.
Yeah.
But then the result of it is that I've subsequently learned that river valley was the outburst of Glacial Lake Agassiz.
Right.
So where you and I went, where the Big Stone Lake, where we stopped there at the bird sanctuary, that was the outburst point, and that carved this huge channel across southern Minnesota, discharged into the Mississippi River. I later found out that, some bona fide geologists, paleohydrologists, had studied that. They called it Glacial River Warren. The estimated discharge of that was 4,000 times greater than the modern Minnesota River.
Wow.
And that's where I really began to learn about what is called an underfit river. And in this program I've got here, I've been documenting rivers all over North America that are essentially flowing in these gigantic fossilized channels.
Right.
Virtually every river in North America.
Yeah. So the channel speaks to a former, much more massive river, and in
Much
it
more
is a
massive
remnant.
river.
Yeah,
Yes.
yeah, yeah.
I don't know if I could even.
I wanted to, but hang on, I wanted to ask you more about you.
Oh.
I think what you represent is the, as others here, and as I myself represent, is the ability of the so-called layperson to bring real insights and knowledge to a field that is dominated by academics.
Yeah.
You know, their day job is to be geologists or archaeologists all the time. You have another day job. You're a builder, if I'm correct.
Yeah, I followed my father's footsteps and became a builder.
Yeah, yeah. And is that still an important part of your life?
Well, I'm semi-retired from that.
Yeah.
You know, from the heyday when I was doing million-plus projects, we're doing, you know, $100,000 and $200,000 projects. Now,
Right.
much smaller crew, which gives me a lot more time.
To spend on these mysteries.
Yes, exactly.
Yeah.
In fact, if
But
I
in a
had,
sense, you've devoted your whole life to these mysteries.
yeah, well, all of my spare time.
You've walked the walk.
Yes,
again
since the
and again.
70s,
Yeah.
all of my spare time is
Yeah.
spent researching, studying, and then in the 90s is when I really started doing the field explorations earnestly. And, you know, Bradley and I have,
Yeah.
you know, traveled a lot together, and we figured up recently, I was talking to him, and we've covered now close to 200,000 miles
Wow.
in the field.
Yeah.
In the field.
That
over
is
the last
walking the walk.
25 years.
Yeah.
Maybe 3,000 or 4,000 scientific papers.
Yeah.
And, you know, we've been out in the field with numerous geologists
Yeah.
on geologist guided tours. So I've had a chance to spend maybe, you know, 3 or 4 days out in the field with different geologists with different points of view, asking them questions. So I figure it's probably just as valuable as sitting in a classroom.
You bet.
With, you know, 50 other students listening to a professor drone on in the front of the of the classroom.
Exactly. That's the point I want to make, really, is that all of us here in this room who have curiosity and a passion for the past, we are all capable of bringing something to it. It cannot be left in the hands of the academics. They do have a role to play, and it's a useful
Absolutely.
role, but it cannot be left exclusively in their hands. We cannot have small groups of academics who claim a monopoly on the story of the human past. And everyday people who've not got those letters after their names are the people who are making the breakthroughs in this field.
Motivated by curiosity
Yeah,
and just wonder of how things actually work.
yeah, that's right.
This is a PowerPoint show that I've been working on, and essentially what I'm trying to do is widen the net and show we can see mega flood features all over North America.
Right.
Now they're very spectacularly displayed in the channel scablands out there, but they're all over.
Right.
So
Let's have a look at some of it.
what?
Let's have a look at some of it.
Okay, let's see what we got. Turn around a little bit here. Okay, I'm going to get to the visuals. Okay, so this is your, and then you're welcome to this graphic. I just took a map and created the ice sheets on it. But you can see there the Cordilleran and the Laurentide. They were two ice sheets that coalesced during the late glacial maximum. And then during that warming period between the older Dryas and the younger Dryas, they melted back a little bit. And that's when the corridor opened up that Graham has mentioned, you know, is kind of the pretty much the standard model. That the peopling of North America was through that corridor.
Through that supposed ice-free corridor. Yeah.
Or ice-free corridor. And hey, there probably was some migration in there.
Yeah.
But, so here I'm kind of showing places where we can document gigantic flows of
So
flood.
by no means limited to the Pacific Northwest.
Correct. Let's
Yeah.
see if I can get the, yeah, okay, so let's see. I was having all, there. So Missoula floods right here. But then you've got the Athabasca floods that came out of this area of the of the Canadian Rockies and flowed down here and then carved out what is the valley that is now occupied by the Missouri River. Here's the Bonneville flood. So this is going to be, in this tour we're going to be starting here by Great Salt Lake, and we're going to be following the route of that flood. This is not a very, there we go, up through the Snake River Plain. Hell's Canyon is right here, and Tammany Bar that I was talking about earlier is right here. And that's where the Great Bonneville flood met the mighty Missoula flood. Then we have mega floods evidence all over the Southwest. In multiple places. We have mega flood evidence in the southern Appalachians, that you're going to see some amazing pictures of in a minute. What I'm calling the Ontario mega floods, the Superior floods. Now these floods would have been the floods that I was just talking about, that you and I were looking at, the potholes, the giant potholes. And then the Lake Agassiz super flood, and this is the one that dates at 12,900.
Right.
And it also flowed out this way.
The Mackenzie River, yeah.
Up here. Mm-hmm. So glacial Lake Agassiz filled all of this basin.
Yeah.
Now, I've been sitting on this for years, waiting for the right moment. But we have a series of very deep lakes, starting with Great Bear Lake. Come on here. There we go, here. Lake Great Slave Lake, which is the deepest lake in North America. Mm-hmm. And if you look at the landforms around here, they're all gigantic erosional features.
Yeah.
You've got channels that were carved, massive channels that actually dwarf some of the stuff we see. Mm-hmm. And then we have drumlin fields. We're not going to probably have time to talk about drumlins today, but I think the drumlins and the work of John
Shaw's work on the drumlins and the subglacial floods as well.
Yes, yeah, because there's clearly evidence of really, really huge subglacial floods.
Yeah.
And
this is a key point, that water flows under the ice cap and can destabilize the ice cap. And
talking about like the Bonneville flood, I mentioned that the most likely source, in fact, the only logical source for that sudden rapid filling of Lake Bonneville would have been extreme rainfall. Yeah. Right? Then we were talking about large erratic boulders being rafted on icebergs, and that those icebergs are being carried in massive volumes of flood water. Mm. Well, so we have to come up with some kind of a scenario where we can simultaneously create the huge boulders that you said, like hundreds, even thousands of them strewn throughout the pathways of the flood. Yeah. We have to produce thousands of huge icebergs. We have to produce volumes of meltwater sufficient to float icebergs. The one up here where it says the Athabasca floods, there is an 18,000-ton erratic sitting just south of Calgary that was iceberg transported, right? The iceberg that transported that boulder had to have been the size of a tanker ship.
Yeah, that's right.
And so you're talking about flows of water that could float an iceberg the size of a tanker ship. Yeah. Now, the erratic, that particular erratic boulder, it's called Okotoks, which I think was Blackfoot for big rock, right, is one of hundreds of a train of these meta-quartzite boulders that reach from where the Athabasca River comes out roughly a little bit north of where the Arrow is and stretches for 500 miles down into Montana. Right. Right? That metaquartzite boulder comes from Mount Edith Cavell, which is on the western side of the Continental Divide. But the fragments, these gigantic fragments of that mountain, are strewn on the east side of the Continental Divide. Yeah. So we have to come up with a scenario where we could quarry tens of thousands of tons of these metaquartzite rock from Mount Edith Cavell, transport it over the Continental Divide, and spread it out in a train 500 miles long. How do we do that? Well, this is where we go back to Warren Hunt, because he believed that the passage of a very large extraterrestrial object would cause seismic shaking that would then cause the fracturing of the shoulders of these mountains onto the ice sheet. Now we have to add to that within that same instant, almost, geological instant, we're simultaneously fracturing huge volumes, coring huge volumes of rock from these mountain shoulders. we're fracturing the ice sheets, we're melting the ice sheets, and now we've got this outflow. What I'm calling the Athabasca floods there is the result of this. And I don't know how you come up with an explanation where all those things could be happening simultaneously. The fourth thing that you would add into the mix is instantaneous sublimation of huge volumes of meltwater directly into vapor.
Yeah.
Which we now know is being modeled through the study of oceanic impacts.
Yeah.
That there would be large-scale injection of water vapor that then is going to rain out over days to weeks.
Yeah, yeah.
Those
Those are the kind of levels of rainfall that we witness on the body of the Sphinx, actually.
Yeah.
As well. Yeah.
And
we're going to have to stop fairly soon.
Who said that?
That was me.
Well, I tell you what we'll do. If we got 5 more minutes.
Yeah.
So here's Lake Agassiz. And if you look at the bottom right here, that outlet, that's where Graham and I visited, where the birds say, right at that point, right there. And then that flowed out and created the Minnesota River Valley that's right in here. And then we went up to where this arrow is, that's at the St. Croix, and that's where we saw the potholes.
Yeah.
But you can see the size of Lake Agassiz.
Enormous.
And then to the north, it drained out into the Arctic Ocean catastrophically. Now, what I would say, if I was in a debate with Flint Dibble, I would point out that we have tens of thousands of square miles of stuff like we just saw here. And I would say, Flint, how many of you archaeologists have excavated into this? And are you going to tell me that you know for certain there's no fragmented pottery there, or that there's no evidence of human? Because no, you have never.
They've never looked.
They've never looked.
Yeah.
Just like when you were talking about with Al Goodyear.
Yeah.
They never look. So they're certain, they're convinced in their own minds, they know that there's nothing there.
That's when archaeology becomes a religious faith.
That's where yes.
A cult.
This is Okotoks, the big rock, 18,000 tons. And what we can say about this is, kind of using our forensic geological skills, is that this was it was a single rock dumped onto the ice sheet. It was transported 500 miles from its place of origin, dumped in the prairies of western Alberta, right here, and it sank. You can see it sank into the alluvium.
Yeah.
So you had deposition of soft alluvium. This would have actually, the final stages of this process would have been relatively gentle because it's sitting on a huge iceberg. And that iceberg is now melting away over many seasons.
Right.
And gradually setting down this 18,000-ton rock into the landscape. So this was a completely independent flow of the Missoula floods.
Right.
And then when you get down where it crosses into Montana, you have this, the giant current ripples.
Yeah.
And that white line there, that's a mile long.
Wow.
So that gives you the
scale
wavelength.
of the thing. Yeah.
And then what that does, it leads right into a huge valley that is the Missouri River. And then all over the Midwest, we have what are called boulder lags, catastrophic meltwater floods circa 12,000 before present, drumlins.
Yeah.
And I think the drumlins are going to end up being a key to deciphering this.
I agree.
And I think through the study of the drumlins, we're going to be able to pinpoint epicenters of impact in the ice sheet.
Yeah.
Let's just. Okay, so that's looking into the modern Missouri. You see the modern Missouri River in there. Now you can look at the channel it's flowing in.
Right, right.
That's classic.
That's
case
what you mean
of
by an underfit.
underfit river.
Yeah.
And then I guess we'll stop with this one because this is spectacular. This, you can see here, this is a gigantic flow. This is Lake Superior. This is like Great Lakes flowing over the Midwestern landscape and carving these fluvial forms here. And then you can see like this would be, let's see, is that I believe that's the Mississippi right there. But you can see that if you look up here, these would have been temporary islands. And prior to the meltdown, these would not have been isolated islands. The strata would have been continuous, let's say, from this to this.
Right.
And all of this intervening area, hundreds of feet of material got washed away. All of this ended up going down, dumping in the Gulf of Mexico, and the city of New Orleans is now built on that sediment.
On that sediment. Yeah.
Yeah.
Yeah. Cool.
So, I mean, there's a whole lot more we could go to
There
here,
is.
but we have to stop.
We could spend the entire evening
Yes.
talking about it. But thank you. Thank you. Thank you, Randall, for
Oh, I've thoroughly enjoyed it.
for joining
as
me
always.
here. I think we're a team. And this is one of the points I'd like to make, is that the mainstream who dominate teaching in this area and who are so hostile to alternative points of view, they're actually very organized.
They're very what?
Organized.
They are organized.
They're very organized in advocating their case and trying to destroy other cases. And one of the things that makes me sad is that those of us on the alternative side are not nearly so organized. I think we're by nature chaotic and anarchic people, and that's part of the reason.
Probably so.
But you know what? That's why I called this the fight for the past, because I do think we need to be more organized and
Yeah.
you know, have each other's backs and make sure that these alternative ideas do not get swept away by the flood of nonsense emanating from the mouths of archaeologists.
Well, I get the impression that there is a sort of a sense of desperation.
Yeah.
Because on some level they know, because the evidence is too overwhelming now. It continues to accumulate year by year, to the point where, you know, I listen to the extent that I'm capable of listening to some of these guys, I don't hear it. They're not addressing any of the points we're raising.
No.
Other than just dismissive. Well, that's nothing. You know, look, if you're going to go into battle here, you're going to have to do better than that.
Yeah.
Because you're going to lose, and I think in the end they're going to lose.
They are losing. They are
losing
the argument.
And I think that they're aware of that, and so they're.
I hope within our lifetimes we'll see some change.
Yeah, I'm thinking the next 5 to 10 years.
I think so too. I think we're coming to a critical moment.
Yeah.
And when critical moments come, and you're in the midst of them, you don't often see it.
Right.
You see it in the rear view mirror.
Yeah.
Thank you, Randall. It's been a very enjoyable
Thank you, Graham.
Thank you. Thank you. Thank you. Thank you, guys. Thank you.